Hi, everybody. Today I want to talk about calculating the area of a region that's bounded by two curves. So it's kind of between two curves, and those are two functions of x. So the kind of thing we're thinking about here, if I've got maybe a curve here and a curve here, what's the area in between these two curves? That's kind of the idea. Now this will be somewhat straightforward, actually, which is kind of surprising, I suppose. What we're going to do is we're sort of saying, all right, so far what we have is the area between a function, that's one curve, the x-axis, and between 2 points A and B. So we kind of have this area right here. That's what we're sort of set up now to calculate. And the way that we did this is we sort of said, oh, we slice it up into small little slivers. Each of those slivers, we make them smaller and smaller and smaller. And in the limit, we get the actual area underneath this thing. And so you're slicing these things up and just sort of dicing them into little rectangles and then saying, oh, well, if I take the left endpoint or the right endpoint, those rectangles have a certain area. I add that all up and that's going to be the area that I'm interested in. Well, now I let those slivers get smaller and smaller and smaller. And as the thinner they get, the closer to the actual area they are. So in the limit, they are the actual area. So that's how we ended up getting this integral, the definite integral from a to b of f of x dx. So that's how we find that. And remember, this is just by that fundamental theorem of calculus, an antiderivative, and you evaluate it at b, you evaluate it at a, you subtract the two. You take the a away from the b part, and then that's what you get. Okay. So that's for one curve. So now the question is, what do I do if I have two curves? So now, oh, well, maybe we can do something with what we already know. So thinking about this, if I have two curves, f of x on the top and g of x on the bottom. So let's sort of think about this. I've got f of x up there. Maybe I have g of x down here. So my g of x is here and my f of x is up top. How am I going to find the area between these two curves? And notice, I really need more information than just what's the area between these two curves. I basically need to say, oh, what does it mean to be between? So when I say between, what am I talking about? I'm talking about where they intersect. And in this case, the G is going to be below the F. And that's a little bit tricky because you could also say that it's between the curves if it's beyond that intersection point. But we really do mean in sort of bounded by those two. And that other area is going to be an unbounded area. It's just sort of just going to go shoot off to infinity on both of those. And you get a bigger and bigger area. So the area of the whole thing is just infinity, right? It's essentially bigger and bigger and bigger the bigger you get. But here I do want the area between. So the A I'm going to take is here, and the B I'm going to take is here. So those are the two limits of my integration. And now I can sort of do something kind of maybe a little bit tricky. I'm going to look at this and say the area that I know how to calculate is the area underneath f of x, between f of x and the x-axis. So remember, that's what I mean by underneath, is it's sort of between this f of x and the x-axis. So the area I know how to calculate, I'm going to sort of shade this sort of slanty in black. Now, what about the area underneath G? Where is that in this picture? Well, the area underneath G, I'm going to shade it in blue, is just going to be what's inside here. And so what's the area in between these two? It's the difference between those two areas. So you sort of think, I take the sort of big area, the big area underneath F. I take the area underneath G. I subtract it from the area underneath F. And what I am left with is, in fact, the area inside in between the two. Okay. So this is great. This is really great news. It means to find the area between two curves is not too difficult. All I have to do is find the area underneath the upper function, that's the one that's on the top, and subtract off the area underneath the bottom function. So that's the one down below. That's the g of x in this case. Okay, and I can even rewrite this in a single integral, right? So they have the same limits of integration. You're integrating with respect to the same variable. So all I really have here is just the area of the top function minus the bottom function integrated with respect to x. Okay, this is really cool, right? So basically now we can make this a little bit more precise. So sort of look at that. So we break this, and we can do this by looking at these Riemann sums and taking the limit as the width of the rectangles goes to 0. And that's how the book actually does this. But I think it's maybe more straightforward to sort of see this as the sort of top area minus the bottom area. And it sort of makes it a little bit easier to consider in that case. So what do we get here? So I have two functions. I need both of those functions to be continuous. And the f of x is on top of the g of x. So the top function and the bottom function are distinctly defined and well defined in this situation. On an interval a to b, the area of the region between the graphs, bounded on the top and the bottom by f of x and g of x respectively, between a and b, is just this difference in the integral, right? So we got that to that point just looking at the picture, but this is a little bit more precise to sort of say we need them to be continuous functions. They've got to be integrable. So I have to be able to integrate those two things. In other words, if I can't do that, then I'm basically in trouble, right? I can't actually calculate that. So let's think a little bit about this. I'm going to give you an example. So I want to find the area of the region between f of x is 5 minus x squared and g of x is x squared minus 3. And notice it's really between those two intersection points in here. And so what are we going to do? So what we're going to do here is we're going to go into a calculator or a computer program or whatever we need to, and we're going to get the graph of these things. So to graph these things, I can plot, or you can just say graph, or whatever you want to do there. You can actually use a lot of different terminology in this system, at least. And if you've never seen this before, this is wolframalpha.com. It's a really nice way to sort of graph things on a computer. The language in here is not specific. It's not like you have to know the precise terminology to graph the right thing. You can just basically use English language to say, I want to do this, and it will try to interpret it and give you a good answer back, which is really kind of cool. So I'm going to plot these two. So I've got 5 minus x squared. And then I also have x squared minus 3. And I want to look at what this picture is going to look like. Okay, so what you can see here, one of them is a parabola that opens up. That's the x squared minus 3, right? So it has the positive a value, and that's going to open up. The other one is a parabola that opens down. That's the 5 minus x squared. The minus x squared in there, the negative, makes it flip on the x-axis, and then I've shifted it up 5, and so that's why it's up there. So what are we looking for? We're looking for the area between these two curves. Well, the nice thing here is I sort of think, well, actually, I'm kind of thinking I can take the area below the top curve and the area down below and sort of add them up together, and that will give me my area. But with this formula, I don't need to go through that process. The trickiest part here will be, well, what are the two limits that I need on my integration? And that's not even that tricky. All I need to do is solve where these two intersect. So where is 5 minus x squared equal to x squared minus 3? And it turns out that in this case, I go through all the sort of process of solving. And maybe I'll do that because that's sort of maybe a little trickier. So I'll add the x squared across. And I will add 3 across. And I get 2x squared is equal to 8. Divide both sides by 2. X squared is 4. X is therefore the plus or minus square root of 4, or plus or minus 2. So it's between -2 and +2 on the x-axis. And you can eyeball it here. Most of the time you may not be able to. So I just want to be sort of careful about how we calculate that. So the way we're going to calculate it is you set up the equation and solve. You don't want to eyeball it on the calculator or the graph necessarily, because maybe it was like -2.1 or +2.6 or something like this. So it's like I can't quite eyeball it exactly. This gives me the exact precise way to do it. All right. So what does that mean? So that means I'm going to go back. I'm going to take my two curves, and which one's on top, which one's on bottom. And so the idea here, the top one is the 5 minus x squared. It's the one that opens down. The bottom one is the x squared minus 3. They intersect at -2 and 2. So to find the area here, I'm going to take the definite integral from -2 to 2 of the top function, which is 5 minus x squared, minus the bottom function, which is x squared minus 3. And you'll notice I put parentheses around that second term. So I want that to be in parentheses. That minus will distribute through both terms here to give me what I need to actually do this integral. Okay. So here we go. So I'm looking at integral 5 minus x squared minus x squared minus 3 from -2 to 2. I can technically go through and just integrate each term at this point, but it's more worth my while to maybe simplify this. So what do I get? I've got -2 to 2. I've got 5 minus x squared plus 3, which is really just 8 minus 2x squared. So 8 minus 2x squared. And I'm going to integrate this. That's not too bad. So the antiderivative of 8 is 8x. The antiderivative of x squared is x cubed over 3. I'm going to evaluate that between -2 and 2. So when I put this vertical bar with a -2 on the bottom and a 2 on the top, what that means is I plug 2 into the equation. And I get what I get. And then I subtract off and plug in -2 into this equation. And that's going to give me what I need. Okay. And so then now I plug things through, evaluate things, and then end up getting what I need. All right. Good. So the next thing we need to say is, okay, so that's great. I can now do this with two curves, what's on top, what's on the bottom, and then the area between those, the region between those. I go from there. All right. So the next thing is now, it's sometimes more convenient to treat a function as a function of y rather than x. So I have an example here. I've got f of x is x cubed and g of x is x plus 6. And so I sort of think about this x cubed goes through the origin and is sort of this sideways S-shaped thing. And x plus 6 is a line, slope of 1, y-intercept of 6. So way up here at 6 is where it crosses, goes like this. And then somewhere over here, the two intersect. And in particular, they'll intersect at 2. So I plug 2 into the first one, I get 8. Plug 2 into the second one, I get 8. And so this really here is just x equals 2. And this back here is actually x equals -6. So the area I'm interested in is here, Well, notice I'm going to have to break this into two separate integrals if I want to do this with respect to x. And the reason is sort of I don't go all the way down to the cubic function from -6 to 0. So what I need is sort of this -6 to 0 with one function, and that's the x plus 6. And then I'm integrating from 0 to 2, the difference of these two. And so the top function is x plus 6. The bottom function is x cubed. And here it's not such a big pain, but if I do this all with respect to y instead of with respect to x, I only have one integral. And so that makes it a little bit nicer. And so what we're really sort of suggesting here is I'm suggesting maybe instead of going from here to here, what if we think about integrating with respect to y? So instead of breaking this into vertical rectangles, what happens if I break it into horizontal rectangles? So I've got my cubic still in here. This still hits at 6, still goes here and hits at 8. And then goes down. So now I'm sort of suggesting maybe we break this into horizontal rectangles. And here, in this case, the leftmost function and the rightmost function don't change. The rightmost function is always going to be this cubic, this f of x equals x cubed. The leftmost function is always going to be x plus 6. So here, this is going to be one integral. And I'm going to think about this in terms of y. So I want to know where are the y values I want to integrate from. So y here is 0. And then y here is what? So y here I can solve. So y is just going to be, it is 2 plus 6. So y here is 8. So this is actually 2 comma 8. That was my mistake. Sorry about that. So this is not at 8. It's actually at 2 comma 8, right? So it's vertically at 8, horizontally at 2. So my integral here is going to be from 0 to 8. Those are y values. I'm going to integrate these two functions, but I want them all in terms of y. So what I need to do is I take y equals x cubed and I solve for y. Or sorry, solve for x. So I get x equals the cube root of y. And then for g of x, the same deal. So I have x equals y equals x plus 6. And so then I'm going to get x equals y minus 6. Okay. And so now the rightmost function is the cube. So the cube root of y minus y minus 6 respect to y. So I'm integrating this thing with respect to y, and then I'm going from there. All right. And so what is it I'm going to get here? So I'll just integrate this thing. So I look at this as y to the 1/3 power minus y plus 6, integrate with respect to y. Then I plug in 0 to 8. So I can do this. 1/3 plus 1 is 4/3. Divide by 4/3 is the same as multiplying by 3/4. Y to the 4/3 minus y squared over 2 plus 6y. Kind of running out of room here. Let me just erase some stuff. So that's my integral. So the antiderivative is there. And now the question is, what about the evaluation? So now I evaluate between 0 and 8. So here I'm going to plug 8 into this thing. So I'm going to get 3/4 times 8 to the 4/3. Luckily for us, 1/3, 8 to the 1/3 is 2. The cube root of 8 is 2. So that's going to be a nice number. It's not even going to be that nasty. Minus 8 squared over 2 plus 6 times 8. and then I subtract off plugging in 0. But 0 plugged into each of these terms is just 0. So the whole thing is just going to be minus 0. So I'm sort of done with this at the 8ths. 8 to the 4/3 is the cubed of 8, which is 2 to the 4th, which is 16. So I get 16 3/4 times 16 minus 8 squared is 64. 64 over 2 is 32. And 6 times 8 is going to be 48. And then I just go from there, plug things through. 3/4 times 16. 4 and 16 cancel, give me a 4 on top. 3 times 4 is 12. This is 12 minus 32 plus 48. So that's negative 20 plus 48 is going to be positive 20. So the area between these two curves is 28. Okay. And there will be times where I might speed through some of these sort of calculations because I assume that you all can do this. It's sort of an algebra, college algebra kind of skill to have. If you're struggling with that, definitely let me know. We'll talk about it, and I can slow down a little bit as I'm going through it and sort of show you where these things all come from as we're going. Cool. Okay. So you can sort of see we can do that with respect to y, so that you can kind of get with it. All right. All right. So now we can sort of see we can integrate with respect to y. To be precise about this, I've got two functions. Again, this time I have a leftmost function. So that's the one that's on the rightmost function, the one that is bigger than the other one. So this f of x is the right function. The g of y is the leftmost function. So which one's on the right, which one's on the left? The f of x is over here, whatever it might look like. It might be kind of a sideways parabola or something. And the g of x might be here. It's some line, right? I'm sorry, f of y and g of y. So they are functions of y in this situation. And then integrating with respect to y basically just says turn those rectangles sideways. So they're going to go horizontal instead of vertical, which is kind of nice. All right. And then you take the difference of the two to make it the area between the two graphs. Okay. So now to find the area between two curves, I have sort of two options. Either I can think of them as functions of x, take the integral of the upper one minus the lower one on the interval of x values. And those x values either will give them to you, or you may have to find them. And to find them, you might say, oh, where do these two functions intersect? Do they intersect on the left and the right? So they should intersect sort of twice if we're going to do it that way, so that you have a left and right limit on this integral. Otherwise, we could treat them both as functions of y. So if they're treated as functions of y, I'm taking the rightmost function minus the leftmost function, integrating between y values of c and d. So the bottom and the top of their intersections. Again, maybe it's intersections, maybe we've given it to you. And so you can sort of say something about that. And maybe we've given you x values and you just have to find what y value is at each of those points that I'm really talking about. And so then that's it. So there's a couple of options for these things. So try the homework. Let me know as you're doing that if it's going well. If it's not going well, anything you need, and we will see how this goes. All right, thanks.